Hello everybody, welcome back to my Carlo methods. In today's video, we're going to develop a hypothesis test to test for independence of the values coming out of your random number generator. Are they independent? Most certainly not. But do they mimic it? Maybe. Today's hypothesis test for independence will be valid for any continuous one-dimensional distribution. It actually is not specific to the uniform distribution, which is how we're going to use it. We want to test our random number generators. So suppose that capital X and capital Y are IID, independent and identically distributed random variables with some common PDF, lowercase f, and some common CDF, capital F. The PDF is the probability density function, and the CDF is the cumulative distribution function. What is the probability that X is less than Y? If you said 1/2, you're absolutely right. But if you're not convinced, let's show it mathematically. I'm going to show it in two ways. The first way to show this is what I call the math stat or mathematical statistics approach, and that is to compute the probability that X is less than Y by integrating the joint PDF for X and Y over the right region. So I'm going to call the joint PDF for X and Y, lowercase f sub xy, and then we'll have two arguments, one for X and one for Y. But because they are independent, I get to multiply individual PDFs. And because they're identically distributed, there's only one PDF. So this f and this f are the same, but one has an X plugged in and one has a Y plugged in. The probability that X is less than Y is going to be the double integral of this joint PDF over the right region. I've set my integral up so that I have a dx first and then a dy. I could do it the other way. The limits of integration will change a little bit, but it's no big deal. So what are the appropriate limits? I'm going to let the outer variable, the dy out here, I'm going to let y run from -infinity to infinity. So over the whole space. Now, if you're talking about a distribution where y only takes on values 0 to 1, like the uniform 0, 1, or 0 to infinity, like as in the exponential distribution, this will still go from -infinity to infinity. The places where it will zero out will be taken care of by this PDF in here, which is defined to be 0 in a lot of places, in some cases. So for a fixed y going from -infinity to infinity, once you fix a y, I want to let my x values go from -infinity up to y. That is the region of integration to compute this probability. Let's do the inner integral first. It's with respect to x, so I'm going to pull the f of y out front of that inner integral. I'm left with the integral from -infinity up to y of f of x dx. This is how you define the CDF. This is accumulating all the probability from -infinity up to y. And so this is going to be a CDF, the capital F, evaluated at y. So I want you to pay attention to this next trick because we're going to use it over and over and over again. How are we going to do this integral when we don't know lowercase f or capital F? We do know that the CDF, capital F, is gotten by integrating the PDF, and you could get the PDF, lowercase f, back by taking the derivative of the CDF. So I'm going to do a U substitution. I'm going to let U be capital F of X, then du is the derivative of that, which is lowercase f of X, and then we get a dx, the differential on there. So I've rewritten this integral as an integral of u du. Whenever you make a change of variables, you do need to change the limits of integration. I'm just going to leave these question marks in here. I'm not going to change them. I'm going to put the x's back in the end before substituting values in. The integral of u du is u squared over 2. So I'm going to plug the fact that u is capital F of x back in, and we get 1/2 capital F squared of x. And we want to evaluate this from -infinity to infinity. So this is a cumulative distribution function. And so the capital F of 3, for example, is the probability x is less than or equal to 3. If we run all the way up to infinity, we will definitely be less than or equal to infinity with probability 1. And if we go down to -infinity, we will be less than or equal to -infinity with probability 0. So when I evaluate this at -infinity and infinity, I get 0 and 1. And the final answer here is 1/2, exactly what we guessed. So that was the math stat approach. The second approach is a Markov approach, where you might condition on one of the random variables. So the probability that x is less than y, I can fix or give the fact that y has been observed to be a value lowercase y, and multiply by the PDF for y. For those of you concerned that these are continuous and I have a y equals y here, that's okay. The probability that you're going to see y equal to some particular value is always 0, but once it's observed, and that's okay. I'm going to plug this y equals little y in here. I'm going to change out this capital Y for lowercase y. And now the only random thing in this probability over here is the capital X. Capital X is independent of capital Y by assumption. So I don't need this conditional information anymore. I can just drop it because it has nothing to do with the randomness going on the left side of this conditional line. So we're down to the integral from minus infinity to infinity of the probability that capital X is less than lowercase y times the PDF evaluated at lowercase y dy. This right here is the common CDF evaluated at y, so capital F of y. And this is the same integral we came up with before. If you let u be capital F of y, then du is little f of y dy. And we get u squared over 2. We plug things back in. It's the exact same integral. We get 1/2 yet again. The hypothesis test that is the subject of today's video is a runs up and down test for independence. Here are values from a random number generator. I simulated 100,000 values and I only put 21 on the screen because that would be ridiculous. And the order is important. These came out of my random number generator in this order. This was the first number, this was the second, here was the third, here is the fourth and fifth and sixth. So I'm going across rows. What we're looking for in this particular test today is how there are runs going up and down in this sample. So, for example, this first number is 0.44 something and the next number is 0.07 something. So I have begun going down, and if the next number is even smaller than that, I will continue this run down. In this case, it is not. The third number is 0.3 something, and that's greater than 0.07. So here I have a run down of length 1. For this particular test today, don't care about the lengths, but just to see it, this is a run down of length 1. So things turn around here. So you can consider this number as starting a new run going up. So I have 0.07 something, and then I go to 0.33 something, and then I go to 0.88 something. So I'm going up, and then I hit 0.55, so the run up has stopped here. So here is a run of length 3 going up. Again, I don't care about the length of the runs, but just to help us make sure we're on the same page in terms of reading the runs up and runs down, I think it maybe is important to talk about the length. So check out this slide, freeze the video, and count the total number of runs up and runs down. In this slide with 21 values, I have 11 runs up and down. In particular, I have 5 runs up and 6 runs down. So make sure you get the same values as me. In the bigger sample of size 100,000, my total number of up-down runs was 66,669. Is this a good value if we have independence? If we have independence, what do we really expect? Do we expect just up, down, or something different? Let's let x1, x2 up through xn be a random sample, so this means they're independent and identically distributed of size n from any continuous distribution. I'm going to let r sub n be the number of up and down runs in the sample. So before we take the sample, we don't know what rn is. It is a random variable. If we take another sample, then rn is going to be different, so it's changing. It is random. And what do we expect rn to be if we truly have independent values being generated? I did say that I was doing continuous distributions only, and I am, but this could be done for discrete distributions. It's just that you would have to define things a little bit differently, like what happens, how do you count the runs if you start seeing ties, like repeated values? That's not going to happen in the continuous case, so it's a little easier to talk about continuous distributions for this runs up-down test. What do we expect Rn to be? We want to know the expected value of Rn, so let's try to figure this out. Okay, so we have this random sample. I want to get a little more specific on this slide. Suppose that x1 through xn is a random sample from a continuous distribution with PDF lowercase f of x and CDF capital F of x. Remember, random sample means IID, so they are assumed to be independent and identically distributed. And if they're identically distributed, we only need one PDF to describe all of them and one CDF. For I going from 1 to n, I'm going to define an indicator random variable. I'm going to call this I sub I, using a capital I for indicator, but there's many other commonly used notations. You can use whatever you like. And I'm going to define this random variable to be 1 if xi from this sequence up here starts a run, up or down, and I'm going to let it be 0 otherwise. Now, if I want to count the total number of runs, if I want Rn, I can just add up these indicators. Do you start a run? Do you not start a run? Do you start a run? Do you not start a run? So I can write R sub n as the sum as I goes from 1 to n of I sub I. We want to find the expected value of Rn, which means we want to find the expected value of this sum. Expectation is a nice linear operator, so I can pull the sum out. I don't need independence to do that, and it's a good thing because these indicators, as we'll see, are not independent. The indicators are also not identically distributed, as we will see. So let's look at some of them more closely. Note that the first value in the sample that I'm calling x1 will always begin a run. This means that the indicator I1 will always take the value 1. So this is either not a random variable or a boring random variable that takes the value 1 with probability 1. Note that the last value in the sample, xn, never starts a run, even if it's like a turning point for where things are going. So here's an example of numbers. Now, these are discrete, and we're not dealing with discrete ones because we don't want ties, but I thought this would be easier than writing down a bunch of decimal numbers. I just want to show ups and downs. Suppose I have 5217825. It looks like this first value starts a run down. So I1 would be 1, but I1 is always 1. And this second value is not starting a run because the run down is continuing to the third value. But the third value is starting a run up. So far we have I1 equals 1, I2 equals 0 because the second one is not starting a run, and I3 equals 1. And so we keep going, right? And here between 8 and 2, we're going down. But from 2 to 5, we start going up with that last value. But the start of that run is right here, the 2 and then the 5. So xn never starts a run, and that means that the indicator I sub n is 0. Hopefully this random variable gets more interesting. Let's look at the other cases in the middle when I goes from 2 to n minus 1. Okay, so hopefully the other expectations of the other indicators are a little more interesting. Let's let I go from 2 to n minus 1 and consider the expected value of the indicator I sub I. Now, even though the underlying distribution is continuous, the indicator is a discrete random variable. And in fact, the expected value of any indicator is equal to the probability of the thing being indicated. And here's why. It takes on two values, 0 or 1. So it's going to take the value 0 if the indicator is 0. So we're going to get 0 times the probability that I sub I is 0, plus 1 times the probability that I sub I is 1. And this disappears because there's a 0, and we get the probability that I sub I is 1. And this is equivalent to the event that x sub I is starting a run. So the expected value of this indicator is the probability that xi starts a run. This is any run, so there's two events here. This is going to be equal to the probability that x sub I starts a run up, plus the probability that x sub I starts a run down. I claim that there's some symmetry here and that these two are the same, so I'm going to say this is 2 times the first one, but we're going to compute this first one, and you can go through the same method to compute this one to convince yourself that these two are going to be the same. The probability that x sub I starts a run up. I'm going to look at some slots. I'm going to label the slots I minus 1, I at I plus 1, and I'm going to imagine putting numbers in here in a way that x sub I would start a run up. So that means if it's going to start the run up, we need it to be going down when we approach x sub I. This means that x sub I minus 1 needs to be larger than x sub I. But if we're starting a run up, we don't want to keep going down. Once we hit x sub I, we want to go up again. And this means that x sub I is smaller than x sub I plus 1. So basically, this is what it means for x sub I to start a run up. So now I'm going to use that Markov approach where I condition on one or two or more of variables in here. Because I have x sub I in both inequalities, I'm going to condition on that, and you'll see why, hopefully. So I'm going to integrate, and I'm going to write this probability given that x sub I equals some value x. I'm going to multiply by the PDF for x, which is kind of like the probability that x sub I equals x, but it's continuous. That probability is really 0. And I'm going to run over all the values, so dx over here. I'm now going to plug the little x into all instances of capital X sub I. Now I'm going to note that the x sub I minus 1 and the x sub I plus 1 are, by assumption, independent, because we're trying to compute this expectation under the assumption that we do have independent values. Because they're independent of capital X sub I, because these guys are independent, I can drop the given information about capital X sub I. And because they're independent of each other, I can break this up into a product. Okay, so here I've got a probability that an x is greater than a little x, and these have the same distribution, so these probabilities are identical. And you might recognize this as the CDF flipped around. This is 1 minus the probability that xi plus 1 is less than or equal to x. Same thing over here. So this is 1 minus the CDF, capital F of x, quantity squared, times the PDF. There's many things I can do with this. I think I'm just going to square it out. And when I square this out, I get 1 minus 2 capital F plus capital F squared, all times the PDF lowercase f dx. I'm going to run the PDF through and imagine integrating all of these. Here I have the integral from minus infinity to infinity of the PDF, and we know that's 1. Here I have an integral that we already did, although don't jump to that 1/2 conclusion, because that did depend on us plugging in minus infinity to y, and here we're plugging in minus infinity to infinity. So to do this, I'm going to let u be capital F of x, then du is lowercase f of x dx, and we're going to get u squared over 2, and I'm going to leave the limits out for now until I put the f's back in, but before we do that, let's hit the third integral, capital F squared times little f of x dx. This is like a u squared du, and we get 1/3 u cubed, and I'm going to hold off on the limits of integration. I want to put the capital F back in for u. Note that this 2 over here is going to get canceled by the 2 down here. So we now have, for the probability that xi starts a run up, we have 1 minus capital F squared of x from minus infinity to infinity plus 1/3 capital F cubed of x from minus infinity to infinity. Just like we talked about before, as you let x go off to infinity, the CDF always goes to 1 because it is a cumulative probability, and that is representing the probability that a random variable is less than or equal to infinity, and that's 1. And when x goes off to negative infinity, you're talking about the probability that a random variable is less than or equal to negative infinity, and that's 0. So when I plug this in and I plug this in and subtract, I get 1 squared minus 0 squared. And then over here, I get 1 cubed minus 0 cubed. Throwing these all together, we get 1/3. Now this is the probability that xi starts a run up, but remember, the expected value we wanted to find in the case that I equals 2 through n minus 1 was actually 2 times this probability, or 2/3. Okay, so I think we have all the pieces. Remember, the goal was to find the expected number of runs up or down in the sample, and we called that Rn, and we wrote it as a sum of indicators. We wanted to find the expected value, and we pulled the sum out because expectation is a nice linear operator. Now we have different expectations depending on what the index is. It's different at 1, at I equals 1, and I equals n, and the other i's. So I'm going to pull out the first term and just write that down. The expected value of I1 was 1. The last term, the expected value of In was 0. And then for the terms in the middle, the expectation was 2/3, and that's going to repeat 2/3 plus 2/3 plus 2/3. We're going to have that n minus 2 times. And when you do the algebra or arithmetic here, you get 2n minus 1 over 3. So that is the expected number of runs up or down in a sample of size 100,000 under the assumption that the sample is IID. When n equals 100,000, as it did at our sample, we get the expected value. What we're supposed to see, what we expect to see, is 66,666 and a third. For our sample, we observed 66,669 runs up or down. That seems pretty close, but is it close enough? We're going to formalize this with a hypothesis test. By the central limit theorem, we know that if we have IID random variables, x1, x2 out through xn, from any distribution with mean mu and finite variance sigma squared, that the sample mean x bar is getting to look normal as the sample size goes up. There is a formal statement to be made about convergence in distribution, but I'm just going to say approximately normal for this course. We've seen already that the mean for x bar is the same as the mean for any one of them, and the variance for x bar is the variance for any one of them over n. The central limit theorem is usually first stated in terms of sample means, but it can also be stated in terms of sums. The easiest way to see this is to know that for normal random variables, linear combinations are still normal. And this means more than just combining like an x1 and an x2. It could mean taking one normal and multiplying or dividing by a constant, or subtracting or adding. So this x bar is 1 over n times the sum of the x's. So the sum of the x's is x bar times n, and also has an approximate normal distribution for large n. By the way, these are not the x's from the sample. These are actually going to be the i's from our sample. But the mean or expected value for the sum of the x's, if you run an expectation across, you just get n mu. You get mu plus mu plus mu n times. And if you run the variance across, which you can do under the assumption of independence, you get sigma squared n times. This is all approximate for large n. Large n is generally considered in most textbooks to be n greater than 30 or n greater than 40. The actual rate of convergence depends strongly on the underlying distribution that we're applying the central limit theorem to. So we have our number of runs, Rn, is the sum of the indicators, and I'm going to pull off the first one and the last one with 1 and 0, and we get 1 plus the sum as I goes from 2 to n minus 1 of the indicators. These indicators are actually not independent. The x's are, x1 through xn are assumed to be independent. The indicators turn out not to be independent, and you will see why if you stay to the end of this video. So it doesn't appear that the central limit theorem is going to apply here because it applies to IID random variables, but there's actually many, many flavors of the central limit theorem. And there's one that is going to be obscure if you're not a probabilist that applies to so-called M-dependent sequences. And these are sequences of random variables that may have some kind of short-range dependence, but if you break the sequence apart and separate them with some number of terms, these guys over here are going to be independent of these guys over here. So that is way beyond the scope of this course to prove. So I'm just going to have to leave it at that. In the description box below, I will put a reference to this theorem. Our Rn is a sum of non-IID indicators, and I claim by this M-dependent version of the central limit theorem that Rn is approximately normally distributed for large n. We already computed the mean, so we know that normal distribution would have mean 2n minus 1 over 3. To continue, we need the variance. I'm just going to plug this in so we can finish the hypothesis test if that's all you care about. I am going to do the variance computation at the end of this video, but it's quite tedious and you might want to tune out before then. I think it's cool. I would stay. But before that, let's do the hypothesis test. So I've got something that's approximately normal for a large n. And to compute probabilities for normal random variables, we usually standardize them and call that standard normal with mean 0 and variance 1, z. So because this depends on n, I'm going to define a random variable z sub n to be r sub n minus its mean divided by its standard deviation, which is the square root of its variance. For large n, by the M-dependent central limit theorem, this is approximately normal 0, 1. Now I know for a normal 0, 1 random variable, I can put it between the two numbers, negative 1.96 and positive 1.96 with probability 0.95. I can also find other pairs of numbers. These are not the only pairs of numbers that will do that, but the ones that are usually taken. Because Zn here is not exactly standard normal, but only approximately, I'm going to say that this probability is approximately 0.95. If I plug in this big expression for Zn and kind of like solve for Rn in the middle of these inequalities, this is telling me that we expect Rn to be between these two numbers, this 2n minus 1 over 3 plus or minus 1.96 times the square root of 16n minus 29 over 90, approximately 95% of the time. For n equals 100,000, these endpoints of this interval comes out to be 66,405 and 66,927.67. Our sample, we estimated the number of runs up, I'm going to call it R sub 100,000 hat. It was 66,669, so we did fall in this interval. So we have passed this hypothesis test for independence for the values computed by my random number generator, with a lot of caveats. First of all, hypothesis tests don't prove anything. They lend support to one idea versus another. If your Rn falls outside of that interval, know that it should 5% of the time, maybe even more, because this was all an approximate calculation. So I would look at more samples if you fell out of the interval, even if you fell into the interval, to see if you are falling in the interval most of the time. You can use a different percentage, like 90%, which would give you different critical values. It would change that negative and positive 1.96. But this is just a rough test. And I don't know, most people use those values. And actually, most people use 2 in place of 1.96 because everything's so approximate anyway. Now, this is a test for independence of the simulated values, but it is a very, very, very weak test. It should not be used alone to establish independence. It should be used as part of a whole suite of tests where you say, oh, I passed 9 out of 10 of these tests. The reason is similar to this example. Suppose you want to test whether you're truly simulating values from the uniform 0-1 distribution. The true mean mu for the uniform 0-1 distribution is right in the middle. That flat line distribution is perfectly balanced. The true mean mu is 1/2. You may know from a statistics course the way to do a hypothesis test on a mean. You would look at the sample mean x bar and you would say, if this deviates too far on either side from 1/2, I don't believe the true mean is 1/2. Suppose you pass that test and you believe, you have evidence to support that the true mean is 1/2. That has nothing to do with the uniform distribution. I mean, it's the mean of the uniform distribution, but we can be looking at a normal distribution with mean 1/2. So just because the uniform distribution has mean 1/2 and you did a test that the mean is close enough to 1/2, you wouldn't use that as a test for uniformity, and I wouldn't use this test alone for a test of independence.
Hello, everybody. Late night editor here. I realized that I'd completely dropped the ball when I was talking in this video and didn't follow up and make the point that I was trying to make. So here it is. And to make this discussion just a little bit quicker, I'm going to assume hypothesis tests prove things, which they don't. They lend evidence for and against. But suppose you were doing a hypothesis test to test whether or not your sample came from a distribution whose mean is 1/2. If you look at a sample mean and do a hypothesis test, if you fail that test, then you can say this did not come from a uniform 0-1 distribution because the mean should be 1/2. If you pass that test, you also cannot say it came from a uniform 0-1 distribution, but you haven't knocked that possibility out yet with the test for the mean that you passed. So then you might look at testing for the variance of the generator. The variance for a uniform 0-1 distribution is 1/12. And if you did a hypothesis test for the variance of the generator based on the sample variance, and you did not get 1/12, then you might say this did not come from a uniform 0-1 distribution and be done with it. But if you did, you still haven't proved uniformity, but you have more evidence because you have that the mean is right and the variance is right. So then if you go on to another kind of statistic and test for uniformity and continue that, you can build up evidence. Now, I actually wouldn't do any of these things. I would test for uniformity directly. But the point I'm trying to make is in this runs up and down test, this is just one small piece of testing for independence, and you should not do this test alone. So we're going to have another test in the next video and another one after that.
So for those of you that just want to know how to do the hypothesis test and to get the test statistic and the values to check against, we are done. For the rest of this video, I'm going to do the really hairy, tedious variance computation for Rn. And I know some of you might want to tune out, but it's pretty darn cool. This is also where we're going to see that the indicators are not independent of each other. The variance of Rn is the variance of the sum as I goes from 1 to n of the I sub I. We talked in the last video about how if you don't know that these are independent, you can't pull the sum out, so we should rewrite this as a covariance of the sum over I and the sum over j. We also talked in the last video about how the sums can be pulled out, so this is the sum over I and the sum over j of the covariance of I sub I and I sub j. One way to compute this covariance is to find the expected value of I sub I times I sub j minus the expected value of I sub I times the expected value of I sub j. We already did these. We know that the expected value of I1 is 1, the expected value of IN is 0, and the expected value of the others is 2/3. We have a lot of cases to consider, though, like are we doing I1 versus I5 or I2 versus IN? Are we mixing those types of variables? So I'm going to organize these covariances in a matrix. This is an n by n matrix, and the ijth entry is going to contain the covariance of I sub I and ij. I'm going to start with the diagonals of this matrix, where I equals j. In that case, we don't really have covariances, we have variances. Remember, the covariance of I sub I with I sub I itself is the variance of I sub I, and we can compute this by finding the expected value of I sub I squared and subtracting that 2/3 squared. We already computed this expectation. The expected value of an indicator squared is going to be 0 squared times the probability it's 0 plus 1 squared times the probability it's 1. This is just the probability it's 1, which is what it was when we didn't square it, because the indicator squared is the same thing as the indicator not squared. So we know the expected value of I sub I squared is 2/3, at least if I is not 1 or n. The variance of I sub 1 is the constant, 1, and that has no variability. So that variance is going to be 0. I sub n is 0, and that has no variability, so that variance is going to be 0. But as for the rest of the elements on the diagonal, the variance of I sub I is going to be 2/3 minus 2/3 squared, which comes out to be 2/9. So we're filling out our covariance matrix, and it's beginning to look like this. I think we can knock out some other rows and columns pretty quickly. Let's consider the case where I is 1 and j is anything greater than 1. And actually, let's first consider when j is n. When j is n, I sub j is 0. So when you're trying to compute this covariance, you have an expectation of 0 minus an expectation times an expectation of 0. The whole thing is 0. When I is 1, when we're in the first row of that matrix, the last value, the last column, has a 0 in it. As for the rest of the first row, so we've got zeros on both ends, the covariance between I1 and ij is the expected value of I1 times ij minus the expected value of I1 times the expected value of ij. I1 is 1, so I can just drop all this stuff. We get the expected value of ij minus the expected value of ij, and that is 0. So I'm going to get 0 all across the top row of the matrix. And while we're at it, covariances are symmetric, so I'm going to get zeros all down the first column of the matrix. In fact, you only need to fill in the diagonal and maybe the upper triangle or lower and multiply those values by 2 to get the total sum for the variance of Rn. While we're here, we know I sub n is 0, so anything, the covariance of anything with I sub n is going to have to be 0 because I sub n is going to be in both those expectation terms and it's going to be 0. So we've got even more done already. Let's consider just off the diagonal. Let's consider the covariance between I sub I and I sub I plus 1 when we're already away from I equals 1 and I equals n. So assume that I is greater than 1 and j is I plus 1. The covariance of I sub I and I sub I plus 1 is this expression here. We know both of these are 2/3, and we need to compute this. So we need to compute this expectation. This is a product of indicators and we'll only take on the values 0 and 1. So I don't really need this many lines to describe it, but I can write this expectation as 0 times the joint probability that both indicators are 0, plus 1 times 0 times the joint probability that the first indicator is 1 and the second is 0, plus 0 times 1, and finally 1 times the joint probability that they're both 1, and all of these disappear except for this last term. So cleaning this all up, we have the expected value of I sub I times I sub I plus 1 as the joint probability that I sub I is 1 and I sub I plus 1 is 1. These indicators are 1 if the corresponding x's start a run, and they can be up or down. So this probability is the same thing as saying that xi starts a run and xi plus 1 starts a run. And now we have 4 cases to consider again. That is, xi starts a run up and xi plus 1 starts a run up. And then we have the case up, down, up, and down, down to consider. I'm going to call these terms A, B, C, and D, and I'm going to put these blocks around those letters to be really clear what I'm referring to here. Let's look at the A term first. The probability that x sub I starts a run up and x sub I plus 1 starts a run up. I'm going to lay out some slots here labeled positions I minus 1, I plus 1, and I plus 2. And I just want to write an example of what this might look like. So I'm going to use integers even though this test is only for continuous distributions. If we had integer value distributions or discrete distributions, we would have to worry about ties when the run is not going up or down, but when you have repeated values, which is a whole separate thing. So these are supposed to be continuous, but I'm going to use integers to show the up and down. It's a little easier than writing the 0.88713 and then the 0.04 whatever. So this is just for up and down, but these should not be integer valued. I'm going to plug something in for x sub I, say the number 5. Now if I want x sub I to start a run up, that means it can't be included in a run up that has already started. So that means it has to be a down from the previous one, which means in the I minus 1 slot, I have to put something larger than the 5. This is, you see us going down, and then x sub I, to start the run up, I need to put something larger than the 5 on this side as well. So this is like a scenario where x sub I starts a run up. But we want x sub I plus 1 to also start a run up. We're already going up, 5, 6. We can start a run down at I plus 1, but we can't start a run up because we're already on our way up. And this means that the probability we care about here is 0 because this just can't happen. We get the same result for D, where both x sub I and x sub I plus 1 are supposed to be starting runs down. So out of those 4 terms, 2 of them are 0. We're off to a great start. Okay, so let's look at term B. Term B was the probability that xi starts a run up and xi plus 1 starts a run down. So again, I'm going to visualize this with slots or positions for the random variables, and I'm going to put in integers even though they're not integers. I'm going to put in a number for x sub I, say 5. Now, if 5 is starting a run up, the number after it has to be higher, and the number before it has to be higher. Otherwise, it would already be like in the middle of a run up, and it wouldn't be starting the run up. If x sub I plus 1 is supposed to be starting a run down, I need, starting from here, to go down, so I need to put something smaller than this 6 over here. So that's the idea. So now let's write this out. What we need for this event to occur is we need x sub I minus 1 to be greater than x sub I, and we need x sub I to be less than x sub I plus 1, and we need x sub I plus 1 to be greater than x sub I plus 2. So we need all these things to happen. To compute this, I'm going to use that Markov approach. I'm going to need to condition on more than one variable here. So I'm going to pick the variables that appear the most. For example, I've got x sub I appearing twice in here, and I have x sub I plus 1 appearing twice in here. So I'm going to put in a little x for x sub I and a little y for xi plus 1. And we get this probability given that x sub I is x and x sub I plus 1 is y times the PDF, which is kind of like the probability, but not really, f of x and f of y. I'm going to integrate in either order. I'm just going to pick dx dy, and let's run with it. First thing I'm going to do is plug in these numbers, plug in the little x and the little y. Then I'm going to say the remaining x's over here, under the assumption of independence, which is how we're running this test, are independent of the random variables over here, so I get to drop this stuff. Okay, so let's deal with this little x and little y in here. There's nothing random there. Let's take this aside and talk about a random variable x. If you want to compute the joint probability that x is, say, between 1 and 3, and the number 5 is less than the number 8, that's just the probability that x is between 1 and 3. The number 5 is less than the number 8, and adding that doesn't add anything to the computation. But if you want to compute the joint probability that x is between 1 and 3, and the number 5 is greater than the number 8, that's not happening. That probability will be 0. So these two numbers here without random variables are really going to zero out this probability in some cases, and in the other cases, we just can ignore it. So to zero it out in some cases, that's going to define the limits of integration for us. In the order I used here, I have dx first and then dy. So you can imagine y going from minus infinity to infinity, but x has to be less than y. So I'm going to change the x limits of integration from minus infinity to y. And now I've taken care of the little x less than little y, and I can just drop it. And because these two random variables are identically distributed, independent and identically distributed, by independence, I can factor this. And by identicalness, I can describe both of these using the same CDF. So the probability that xi plus 2 is less than y for a continuous random variable, this is the same thing as saying xi plus 2 is less than or equal to y, which is defined to be the CDF capital F of y. Over here, I've got 1 minus the CDF capital F of x, and so we've got this integral to compute. My x integral is first, so I'm going to pull the y stuff outside of the x integral, and let's consider this part. I'm going to multiply this across. You don't have to do that. You can do a different kind of u substitution, but I'm going to multiply this across. The first integral is going to be the integral from minus infinity to y of little f of x dx. That's the PDF, and that's precisely how you compute the cumulative probability, which is capital F of y. The second integral here is going to be capital F of x times the lowercase f of x from minus infinity up to y, and this is the u substitution integral. We know that this is 1/2 times the CDF squared, evaluated at minus infinity up to y, and the CDF at minus infinity is 0, so we get 1/2 f capital F squared of y. So that's just for this integral here, so I'm going to plug it in. Not only am I going to plug it in right here, but I'm going to multiply those two terms across, and our b term now becomes this integral minus this integral. B's are more of those easy u substitution integrals, where in both cases I can let lowercase u be the CDF and du be the PDF dx. This is really similar to what we did before, so I'm not showing all the u substitution details, but we end up with 5/24. So this is the b term out of a, b, c, and d, or the expected value of x sub I times x sub I plus 1. Remember, the expectation of that product is the joint probability that I sub I is 1 and I sub I plus 1 is 1, and we broke that into 4 terms. We determined that 2 of these have probability 0. We just figured out that this term is 5/24, and I claim that there's symmetry here, and this term is also 5/24, but if you don't believe it, you can go through the conditional argument and check it out for yourself. So this entire sum comes to 10/24 or 5/12. This is not the covariance we want. This is just this part of the covariance. The covariance between I sub I and I sub I plus 1 is this 5/12 minus 2/3 times 2/3. And this turns out to be negative 1/36. So that's going to be the entry above and below the diagonal. And right here, we have proven that the indicator I sub I is not independent of the indicator I sub 1. If the covariance was 0, they could be independent. They could not be independent. But if they are independent, the covariance must be 0. And we're saying a covariance that's not 0, so I know they're not independent. I'm going to spare you the rest. What we end up having is 2 to the 9th down the diagonal, and there's n minus 2 of those terms. We have this negative 136 down the off diagonals, and if you count those up, there's n minus 3 terms on both sides, so we get 2 times n minus 3. If you then look at the next term, which is the covariance of x sub I and x sub I plus 2, you're going to have to do the same sort of conditional argument. It's going to be a little messier, but you should get 1/180, and there are n minus 4 of those next off diagonal terms, and there's n minus 4 on the other side of the diagonal, so we get 2 times n minus 4 of those. And once you go further, you get a covariance of 0 between xi and xj. So adding these all together gives you the 16n minus 29/90. Okay, so that concludes today's video, which was a hypothesis test for independence based on the number of runs up and down in a random sample. This test works for any one-dimensional continuous distribution, but it is not a good test to use alone for the same reason that testing whether or not your sample has a mean of 1/2 is not a good test for uniformity. By the way, if you'd like to see that central limit theorem in action for the number of runs up and runs down, check out the description box below, where I have Python and R code. In the code, I produce many samples of size 100,000 uniform 0-1s using a built-in random number generator. I repeatedly compute values of Rn. So my first sample of size 100,000 might have an Rn of 66,669. My next sample might have an Rn of 66,652, and so on. If I compute those many times the value of Rn and make a histogram of those, we're going to see the bell curve. We're going to see the normal distribution. So check it out. It's pretty cool. And I hope to see you in the next one.